In 1905, Albert Einstein derived E equals mc² by tracing the logic of a single specific thought experiment involving a floating object and a flash of light. Imagine for a moment you are a stationary observer, watching a metallic probe float perfectly still in empty space. Without warning, the probe emits a bright flash of light, radiating in all directions at once. Light carries energy away from its source. As concentric rings expand, the probe's internal energy drops by the exact amount contained in the flash. Because the light was emitted symmetrically, providing no directional thrust, the probe doesn't recoil. Its velocity remains zero. From this stationary perspective, the math is simple. The object loses energy to the light, but its position and speed are unaffected. Now, imagine watching this same event from a different perspective, inside a spaceship flying rapidly past the probe. From inside the ship, you feel stationary. Looking out the window, the probe is the object that appears to be flying past you. Because the probe is moving relative to your window, you calculate that it possesses kinetic energy, the energy of motion. But special relativity tells us that time passes at different rates for you and the probe. This affects how you measure the energy of that same flash of light. Due to the relativistic Doppler effect, a moving observer measures the light's energy as slightly higher than a stationary one. Specifically, the energy is multiplied by a factor determined by the observer's velocity. This shift in measurement creates a conflict between the perspective of the stationary observer and the perspective of the moving observer. We can pinpoint the nature of this conflict by looking at two different ways to observe the same event. In timeline A, you accelerate to your cruising speed first, then watch the probe flash its light. Because you are moving during the flash, you measure that extra Doppler energy leaving the probe. In timeline B, you watch the flash while you are still stationary, then you accelerate to your cruising speed. Here, you measure the standard amount of energy leaving the probe. Since you never physically touch the probe in either case, the final total energy must be the same, regardless of the order in which you chose to move and watch. Because timeline A measured more energy leaving the system during the flash than timeline B did, the remaining kinetic energy at the end of timeline A must be lower to compensate and keep the totals equal. This creates a paradox. The probe's kinetic energy at the end of the experiment changes depending on when the light was emitted. To understand this, look at the formula for kinetic energy, 1/2 mass times velocity squared. The light was emitted symmetrically, so the probe's velocity remained exactly the same. This kinetic energy decreased, but velocity is constant. The probe's mass must have changed. For the conservation of energy to hold true across different perspectives, the object's mass must decrease at the moment it releases the energy of the light. Balancing the energy between those timelines reveals the change in mass equals the energy divided by the speed of light squared. This is the derivation of E equals mc². This means mass and energy are not two different things, but two ways of measuring the same substance. Whenever an object radiates energy, it is physically losing a portion of its mass.